So hello everyone again. This is lecture 3 part 3 of current electricity. Today we will go on with the further discussions of resistivity of different materials. So let's not waste any time again. So I am Samir Lavankar. Let's begin our discussion. So right now let me try to give you the course outline of whatever things are completed till now. So in the introduction portion we went with the concept of why the current electricity is being involved when the movement of charges happen. Then this has to be flowing in a separate form. There should not be something called as lightning occurring, because if the lightning would have occurred then it is not uniform and hence cannot be taken into good use. Efficiency would be very poor if something called as lightning would have occurred. So therefore we try to streamline everything, and that is the complete concept of current electricity which are taking into picture here. The next concept of electric current, in which we understood the mathematical formulation of electric current, which is equal to small q by t, and in infinitesimal method we understood that concept equal to delta t, limit delta t tending to 0, del q upon del t. In the third concept of electric current in conductors, we understood the concept of materials having names called as conductors, semiconductors and insulators, and we understood that why the electron bound is much more free in the conductors, followed by semiconductors and insulators. In the Ohm's law we understood a relation called as V is directly proportional to I, which is equal to IR, and finally R is directly proportional to L by A, and hence we got R is equal to rho L by A. So these all things were being understood. A concept called as J was being understood, which has the units of capital I by A, that is current per unit meter square area. And finally we understood a concept called as conductivity, which is equal to J, which is sigma is equal to 1 by rho. Okay. Then in the fifth concept we understood a concept called as VD, which is equal to minus small e capital E by m into tau, and origin of resistivity was being dealt with here. So in the final concept, in the previous lecture we understood the concept of limitations of Ohm's law, in which we found out that there were 3 limitations which were happening in substances such as gallium arsenide and diode, and there may be some devices or some materials also which does not actually accurately follow the concept of V directly proportional to I. Finally, we are in the seventh point here, that is the resistivity of various materials. So in the resistivity of various materials we understood the concept that the resistivity of the conductors are very less, that is of the order of 10 to the power minus 8, and the resistivity of materials such as insulators are very high, which is of 10 to the power let us say 16 or 14. The midpoint area which is between conductors and insulators is something called as semiconductors. Semiconductors are dealt in some another chapter very clear, very in detail, because they are very much useful for electronic devices. How they are used, how the impurity is being added, how are they being useful for the complete concepts of electrical engineering is being dealt in that chapter only. So you may look to that chapter. Right now we will go with the further discussions of resistivity of various materials. Okay. So that is the course outline for you. Almost half of the current electricity chapter is being completed. Okay, so this thing is being dealt with. So now as you can see, this is just for your show purpose. There is no need to mug up anything here. So as you can see that the conductors resistivity keeps on decreasing here, keeps on increasing as we go down. Then finally we have semiconductors in the order of 3.5 10 to the minus 5, something is having 0.46, 2300 and so on, and the insulators are of the order of 10 to the power 5, 10 to the power 10, 14, 16 and so on. So this is the complete concept of resistivity of some materials that wasn't dealt in last chapter. Let us move on with the further discussions now. So now commercially produced resistors for domestic use or in laboratory are of two major types. So basically resistors of two major types. First is called as wire bound resistors and second is called as carbon resistors. So this is a particular typical example of a wire bound resistor, and this is a typical example of a carbon resistor. Wire bound, as the name suggests, as something is being bounded by wires. Carbon, as the name suggests, that the carbon content has to be present in that resistor. Okay. So let me just try to define both the things here, and that is the end of this point also here. So wire bound resistors are made by winding the wires of an alloy. So the alloys which are being used for winding are manganese. So please remember these things: manganese, constantan, nichrome or similar ones. So these are 3-4 types of alloys which are being used to as a material, which are used or bounded across a substance so that the resistor can be made. The choice of these materials is dictated mostly by the fact that their resistivities are relatively insensitive to temperature. That means even if we try to increase the temperature or decrease the temperature, the rho value is approximately same. These resistance are typically in the range of a fraction of an ohm to a few hundred ohms. So something called as 10 to the power minus 2 or 10 to the power minus 3 ohms to the range of let us say 10 to the power 2 or 10 to the power 3 ohms can be obtained in this concept of wire bond resistors. Okay, next point is resistors in the higher range are made mostly from carbon. So, carbons to have major range 2, 3, 4, 5 also. So, resistors in the higher range are mostly made from carbon. Carbon resistors are compact, quite evident. These are very small. These are you can even see the resistor in the motherboard also of your laptop, of your computer, of your mobile phone. Inexpensive and thus find extensive use in electronic circuits. Carbon resistors are small in size and hence their values are given using a color code. So, now what is this color code? Please try to I will try to explain you here. So, this is a typical example, this is a typical table which is needed, which you need to remember for the color coding. So, as you can see that different numbers are being allotted for different colors here, and these also have a multiplier here, and these last three, that is gold, silver and no color, are nothing but tolerances. So, I will try to explain you how this resistivity color codes are being explained using 1-2 examples also. Let me first read everything here. So, the resistors have a set of coaxial colored rings, coaxial as in having the same axis. So, coaxial, as you can see that this can be the axis and these are the color coded resistors. Okay. So, the resistors have a set of coaxial colored rings on them whose significance are listed in the table. Whose significance are listed in the table? Table is this that I already showed you in the previous slide. The first two bands from the end indicate the first two significant figures of the resistance in ohms. That means, let us say for an example of, okay, first of all let me read and then I will try to explain. So, the third band indicates a decimal multiplier, that is 10 to the power how much. Next is the last band stands for tolerance or possible variation in percentage about the indicated values. Tolerance as in how much the value can move on from the initial value. Let us say that value is mean and it can go up plus 5% or minus 5%. Sometimes this last band is absent, sometimes only there are 3 bands involved, then that indicates a tolerance of 20%. For example, if the 4 colors are orange, blue, yellow and gold. So, please not look here, for now let me try to explain you. If the first 2 colors are orange, then it is red, sorry, it is orange, then it is blue, then it is yellow and then it is gold. Okay, so let us go on to the back slide now. So, as you can see orange is the first color which is having a value of 3 here. So, just go here and write 3. The next is blue. So, as you can see blue color is where it is blue is here. So, blue is 6. So, as you can see you can just write it 6 here, you can write 6 here. Next value is yellow. So, yellow as the third, as only the first 2 points are significant digit and third point is the decimal multiplier. So, as you can see yellow has a power of 10 to the power 4. So, as the value of 4 is used, hence the multiplier will be 4. Therefore, that is 36 multiplied by 10 to the power 4, and next is gold color is used. So, gold has a significance of 5%, tolerance of 5%, therefore, it will be plus minus 5%. Hence, the resistance of that particular carbon resistor will be 36 into 10 to the power 4 ohms or plus minus 5% ohms, and this is the complete answer of the previous point which is written here. What does it plus minus 5% means? That means if I try to find the value of 36 into 10 to the power 4 into 5 by 100. 5 by 100. So, let us suppose it gives a value of x, then the range of that particular value of resistance can be in the order of 36 into 10 to the power 4 minus x to 36 into 10 to the power 4 plus x. That is the meaning of this tolerance concept here. Okay. So, just for your example again, just for your practice again, I will try to write the answers for these two also. So, as you can see its first is red, silver. So, as you can see the red number has the value of 2 here, therefore, it will be 2 multiplied by 10 to the power 2. Till third point this thing is being completed, as the last point is having a color code of silver. So, silver is nothing but having a value of 10 tolerance, therefore, the value will be 22 into 10 to the power 2 plus 10% or plus minus 10%. So, this is the tolerance value for this portion. So, A value is explained to you here. Similarly, if I go for the B point here, so first is yellow, violet, brown, gold. So, as you can see yellow is having a value of 4, hence this will be 4 here. 4, then next value is violet, violet is having the value of 7 here, so it is 47 into 10 to the power, next value is brown, brown is having a value of 1, therefore it will be 1 here, and gold is having a value of 5%, hence the tolerance will be 5%. It is equal to plus minus 5%. So, yellow, violet, brown, gold. So, yellow is having a value of 4, violet is having a value of 7, brown is having a value of 1, and the gold is having a value of 5%. Hence, these are the 3 examples I explained to you how the color coding is being done for the carbon resistors. So, this thing is also being explained. Let us move on to the new concept now after the resistivity of various materials, which is called as temperature dependence of resistivity. How the resistivity of a substance is depending upon the temperature. Do it increase, decrease, or what happens? Let me try to explain you in this slides. Okay. So, the resistivity of a material is found to be dependent on the temperature, quite evident, as you can see from this diagram also, that as the temperature keeps on increasing, the resistivity keeps on increasing also. Different materials do not exhibit the same dependence on temperature. Sometimes it keeps on increasing linearly, sometimes it has a non-linear sense. So, if it has a linear sense, then it is some sort of this manner, and if it is having a non-linear sense, sometimes it is given in the question. But for general purposes, we can assume that a linear dependence on temperature resistivity has. Okay. So, over a limited range of temperatures, that is not too large, the resistivity of a metallic conductor is approximately given by, please remember this formula, that is rho t is equal to rho naught into 1 plus alpha delta t. That is rho at some time capital T is equal to rho naught into 1 plus alpha into T at that time minus T naught. What is T naught? T naught is the temperature at which it has a resistivity of rho naught. So, this is the formula, this is the explanation, please try to remember this, that is rho t is equal to rho naught into 1 plus alpha delta t, okay, where rho t is the resistivity of the resistivity at temperature capital T, and rho naught is the same at a reference temperature T naught. Alpha is called the temperature coefficient of resistivity, and from the above equation dimensions of alpha is nothing but temperature inverse, quite evident. As how to explain this? So, rho t by rho naught gives you non-dimensionless value, therefore, alpha into T should also give a non-dimensionless value. So, anything which is multiplied by temperature should have an inverse value of it, and therefore, the value of unit of alpha is nothing but temperature inverse. Okay. This point has also been explained. Let us move on to next point now. So, for metals alpha is positive and value of alpha for some metals at T is equal to 0 degree are listed in table 3.1. I think I have explained you that table also here. So, this is that table. So, these are the temperature coefficient resistivity alpha value given to you. So, as you can see, the value for conductors are in the form of positive sense. That means that it increases, the resistivity increases with the increase in temperature, but it is not the same for the semiconductors. It decreases, it are in the negative sense for semiconductors. So, this is the one more differentiation part in terms of conductors and semiconductors, that the alpha value for conductors keeps on increasing and the alpha value of semiconductors keeps on decreasing. Okay. So, let us move on with the further discussions here. So, for metals alpha is positive and the value of alpha for some metals at T is equal to 0 is also given in table 3.1. The relation of the above equation implies that a graph of rho t plotted against T would be a straight line, quite evident because it is a linear graph here, as you can see. At temperatures much lower than 0 degree Celsius, that graph however deviates considerably from a straight line. So, what does it try to say is 0 degree Celsius is nothing but 273 kelvins, and this graph is being plotted for the temperature which is less than 273 kelvins. So, when it was found, when it was plotted, it was found that it does not have a linear sense, it has a non-linear way. And what is this non-linear way? This is being explained here. As you can see clearly that the resistivity is never absolute 0 value, it has some velocity, it even has some value at temperature 0 kelvins. Okay. So, this thing is also been explained, it is not linear here, it is a non-linear below 0 degree Celsius. Okay. Next concept is this thing is also been explained. So, above equation can be used approximately over a limited range of capital T around any reference temperature T naught, where the graph can be approximated as a straight line. So, this has to be used for a limited range. For you, for the 12th class purposes, every time that limited range will be always provided to you, you just need to find out either the value of rho t or the value of capital T. So, this has not been in your much greater sense, much detail, you do not need to remember what is that limited range. For now, just need to remember this formula, that is rho t is equal to rho naught into 1 plus alpha delta t. Okay. Next is some materials like nichrome, which is an alloy of nickel, iron and chromium, exhibits a very weak dependence of resistivity with temperature, sometimes it does not even change. Manganese and constantine have similar properties. So, there are some materials which does not show a temperature dependence on resistivity. These materials are thus widely used in wire bond standard resistors, since the resistance value would change very little with temperature. So, because the value of resistance, as resistance is directly proportional to resistivity, we can say that they are having a linear sense. Therefore, we can say that if we take such alloys which are such as nichrome or manganese or constant time, then we can find that can be extensively used, because even if the increase in temperature or decrease in temperature would have occurred, let us say due to some heating or some faults which are happening in an electric circuit, it will not cause a change in the resistance, and therefore, if there is a no change in the resistance, there will be no change in the current, and hence there is a less chance of short circuit happening. Okay. Unlike metals, the resistivities of semiconductors decrease with increasing temperature. So, this I already explained to you, as you can see in the previous table also, that the value of alpha was negative. Alpha value was negative for semiconductors, and because it is negative, it can directly be proved that the resistivity is in the opposite sense of that of conductors. So, resistivity of semiconductors decreases with increasing temperatures, quite evident that if the temperature is increased here, that the value of resistivity will decrease. Similarly, for conductors, the temperature increase, the resistivity value will increase. Okay. Next is we can qualitatively understand the temperature dependence of resistivity. Resistivity of a material is given by, as you know, these are nothing but the concepts which are evolved from the previous concepts of drift of velocity and origin of resistivity only. So, rho is nothing but inverse of 1 by conductivity, which is equal to m upon n e square tau. Rho thus depends inversely on both the number n. So, as we can see directly from this, that rho is nothing but m upon n e square tau. So, as you can see from this formula, that rho is inversely proportional to n and rho is inversely proportional to tau. So, rho thus depends inversely both on the number n of free electrons per unit volume and on the average time tau between collisions. As we increase the value, as we increase temperature, average speed of the electrons which acts as the carriers of current increases, resulting in more frequent collisions. Quite evident, because there will be much more heat. Because of this heat, the electrons try to move apart or move towards each other at a very faster rapid pace, rapidly. So, as we increase temperatures, the average speed of the electrons which act as the carriers of current increases, resulting in a more frequent collisions, and therefore the average time decreases. The average time of collisions tau thus decreases with temperature. Therefore, now what happens is, in a metal, n is not dependent on temperature to any appreciable extent. So, as you can see, a question may occur to you that if the value of n increases, and the value of tau decreases, then due to this sense there should be a decrease in this, and due to this sense there should be an increase in this. So, which value should we take into consideration here? Should we try to say that due to the value of n increasing there should be a decrease in resistivity, or should we take this into sequence that because the value of relaxation time is decreasing, we should take increase resistivity into picture. So, that thing is being explained in the next point here, that in a metal n is not dependent on the temperature to any appreciable extent. So, we can just neglect that concept of n increasing and thus resistivity decreasing, and thus the decrease in the value of tau with rise in temperature causes rho to increase, as we have observed. So, we just neglect, or we can say in that form that the value or the concept of this is not that much powerful to take resistivity into extent here, as the only concept of tau being decreased has been taken into picture, and hence we will find that for metals, please remember, only for metals the value of resistivity increases with temperature. Okay. Next is for insulators and semiconductors, however, n increases with temperature. So, this time what happens is, as rho is inversely proportional to n and rho is inversely proportional to 1 by tau, this time the value of n increases with temperature, and this increase more than compensates any decrease in tau. In semiconductors, the value of n takes its influence. Here the influence of n is very important. Why it is important? Maybe this concept will be dealt in the concept of chapter of semiconductor devices. For now you should remember that here the value of n is very important. Hence, this increases more than this value of tau, and it overcompensates them, the decrease in tau, and therefore we can find that for this rho decreases with temperature. Hence, there is a decrease being found here. So, finally, let me conclude everything here. So, in the concept of temperature dependence of resistivity, we found that for metals, as temperature increases, rho increases. Why? Because there is a relation with tau here, and in the value of tau and capital temperature element T, if temperature increases, resistivity decreases in semiconductor. This is in metals, this is in semiconductors, and this has a relation more for n, which is greater than tau. Okay. So, let me end it here only. This is the end of your temperature dependence of resistivity also. I will move on with this example in the next slide, and that will be the end of temperature dependence of resistivity also. After this we will move on with the next concept of power. So, the course progress for you, we start with the introduction concept, then the electric current mathematical formulation was been dealt with in second point, then the concepts of conductors, semiconductors and insulators have been dealt in third point. In the fourth point we understood a concept called as V is equal to IR and R is equal to rho L by A, with another concept called as J also, and sigma, which is nothing but 1 by rho, that is conductivity, is inversely proportional to resistivity. And in the fifth concept we understood the concept of Vd, that is drift velocity. Then in limitations of Ohm law we found that 3 values, some devices, some materials also which are not following the Ohm's law, which is used efficiently evidently in the electric circuits. Then in resistivity of various materials we understood the concept of resistivity for conductors, semiconductors and insulators. In the 8th point of temperature dependent resistivity. Finally, right now we are on this point only, that is temperature dependent resistivity, and after this thing is completed we will go on with the next point, that is electrical energy and power. So, I think half of the current electricity is being done. Let me make a stop here only. We will continue our discussion in the next class. So, thank you so much.